Hello and welcome to today's webinar. The topic of this webinar is ductwork design. My name is David Pick and I'll be presenting today's program. During this webinar, we will discuss the different design methods for ductwork sizing. We will start with some basic concepts, review some general design criteria for ductwork sizing under rules of thumb, look at ASHRAE design procedures, discuss duct shape selection, pressure class, and duct standards. Touch on some things to remember when it comes to ductwork specifications. And finally, we will wrap up with ways to optimize your duct design. Let's get started with our basic concepts. The first basic concept we'll discuss is pressure. Pressure is the heart of duct design. We'll be discussing total, static, and velocity pressure throughout the webinar today. Total pressure is the sum of velocity pressure and static pressure inside the ductwork. Velocity pressure of an airstream in ductwork can be calculated by taking the square of the velocity divided by 4005. For example, a 1,000 foot per minute velocity divided by 4005 and squared is equivalent to 0.06 inches of velocity pressure. If we change that velocity to 2,000 feet per minute, the velocity pressure increases to 0.25 inches of static, or velocity pressure. As the velocity of the airstream doubles, the resultant velocity pressure will increase by a factor of 4. Because velocity pressure and static pressure are parts of the total pressure, we can exchange velocity pressure for static pressure by increasing the duct size. The transitions will have a static pressure loss associated with it, but for this example, we're going to ignore the transition losses to simplify. The airstream in this example will have a constant total pressure of 1 inch. In the figure above, we can follow the example and watch the exchange of velocity pressure for static pressure as we travel from the left to the right of the figure. So if we look at a 5-inch duct with an airflow of 500 CFM traveling at 3,600 feet per minute with an associated velocity pressure of 0.81 inches and a static pressure of 0.19. If we transition it to a 6-inch duct, the airflow will now be traveling at 2,500 feet per minute. Velocity pressure will decrease to 0.39 inches, and static pressure will increase to 0.61 inches, still maintaining the 1-inch total pressure. If we transition again to an 8-inch duct, the airflow will now be traveling at 1,500 feet per minute. Velocity pressure will decrease to 0.14 inches, and static pressure will increase to 0.86 inches. If you notice in all these different calculations, the velocity pressure and static pressure, as they follow, remains constant, the total pressure, but the velocity pressure related to airflow drops dramatically as we get below 1,500 feet per minute. Some more basic concepts. Unit friction is a standard unit used in duct design. It describes the static friction loss per 100 feet of straight duct run. The units are inches of water gauge per 100 feet. You times the total equivalent feet of duct run by the design unit friction to determine static pressure loss of the section of duct. Aspect ratio applies to rectangular ducts. It is the ratio of width to height of the duct. So a 24-inch wide by 12-inch high duct will have an aspect ratio of 2:1. The duct efficiency goes up per air volume as the aspect ratio approaches 1. Equivalent diameter is defined as the diameter of a rectangular duct that has an equal resistance to flow for equal flow and length. For example, a 10-inch by 10-inch duct would have the same friction loss as a 10.9-inch round duct, or would have an equivalent duct diameter of 10.9 inches. Let's look at the design methods. Standard documented design methods for sizing ductwork include velocity reduction or velocity method, equal friction method, static regain method, and constant velocity method. I find the most common method of duct sizing is a combination of the velocity and equal friction method. The different methods were designed for specific applications, which we will touch on a little further on. Let's take a closer look at the different methods. Velocity method, or also known as velocity reduction method, is generally used on smaller low velocity systems, such as residential or small commercial with only a few offices. This method consists of selecting an acceptable duct velocity at the discharge of the fan and decreasing the airflow at each junction or takeoff. The design will generally utilize standard design criteria for duct velocities based on design office standards. Past ASHRAE handbooks tabled suggested maximum velocities by occupancy and duct type, but have been removed from more recent versions. Equal friction method. This method consists of selecting and maintaining a constant unit friction throughout the design, decreasing duct size after each takeoff to maintain the same unit friction. This method is regularly employed on moderate-sized systems. The designers would select duct size based on acceptable unit friction design standards. Fittings, elbows, transitions, junctions, and takeoffs would be looked up for standard sizes on a lookup table. The table would provide equivalent lengths of duct for each fitting. The total length of ductwork would be summed up for each unit friction and totaled. With the introduction of computer-aided duct design, the lookup tables for fittings waned in popularity, and it has been replaced with computer-calculated fitting losses. A modified equal friction method is still a popular method. Ductwork is sized for unit friction limits, and fittings are calculated using a duct design program. The static regain method. This method consists of increasing ductwork after each takeoff or branch to maintain a constant duct static pressure. Static regain is used most commonly in large or industrial applications. It requires larger ductwork and higher initial airflow velocities. The higher velocities equate to a greater potential pressure to be regained. Smaller systems or systems with lower velocities do not offer adequate potential pressure to be regained to make the system work, and therefore we do not see it generally in office buildings. Constant velocity method. This method consists of increasing ductwork after each intake or branch to maintain a constant duct velocity. You notice that I said intake. That's because the constant velocity method is usually used in exhaust systems. These systems are designed to keep particulates entrained in the airstream. Let's look at the order of utilization. The most common methods of air duct system design are as follows: equal friction, velocity reduction, static regain, and constant velocity. Equal friction is still the most widely used method. It is applied to most moderate to large size systems, large portions of hospital, large retail, education, office, and high-rise residential. Most design firms utilize both maximum unit friction and duct velocity design criteria in concert to size their ductwork. Velocity reduction method. Velocity reduction is used in most small construction that is constructed without professional design services. It is an easily applied method. Examples of this would be residential replacement, small office installation, and interior renovations, not requiring mechanical system design or permits. The sheer volume of this type of work has kept this rule of thumb method common. Static regain is mainly employed in large, high-velocity systems. The higher velocity provides adequate potential static regain to make the design and the added ductwork cost-effective. Due to the higher velocities, the ducts generally cannot be adjacent directly to or directly above occupied spaces. Rooms and spaces with large volumes or high ceilings provide adequate distance, though, for the sound generated by higher velocities in the ductwork to dissipate before reaching the occupants. Such spaces would be athletic stadiums, airports, and conference centers. Regain is regularly used, though, in risers, as the higher velocities allowed inside enclosed chases have adequate energy to be worth the duct cost. The enclosures help to maintain acoustic requirements and keep sound generation from reaching the occupants. Industrial installations generally do not have as stringent of sound requirements. This allows for the use of the higher duct velocities that make static regain design method the choice. Constant velocity. Constant velocity is employed in exhaust systems where minimum velocities are required to convey particulates. The number of exhaust systems with these requirements are not a large part of the construction market. For this reason, this is the least utilized method. While it is the least, that does not mean it is not regularly utilized. These systems often are kitchen exhaust or welding and grinding exhaust systems, which are regularly seen, just not in high volumes. Let's look at our design rules of thumb. The design rules of thumb for duct sizing revolve around two parameters: friction loss and velocity. Most design offices employ a dual maximum design criteria. In large ducts, the velocity will govern the size of the duct. As the duct decreases in size, static pressure will take over and be the governing factor. Depending on your office criteria, there is a changeover point, but it will change depending on those criteria. Velocities are limited in most cases to control noise produced by the ductwork, while static pressure limits are set to decrease friction loss and energy consumption. We will review some values now. To maintain acceptable sound levels, velocities should be adjusted for ductwork depending on installed location. We can see how the allowable velocity increases as the material between the occupied space changes. Velocities should also be decreased the closer they get to supply outlets. You can see the changes from the suggestions for main ductwork down to runouts. These suggested velocities are for straight runs of ducts. Elbows, fittings, and takeoffs will increase duct noise and should be considered separately. ASHRAE provides detailed guidance for suggestions on maximum allowable velocities by Design RC in Chapter 48 of the Applications Handbook. It is a good reference, and I would highly suggest reviewing it for additional information. Static loss. ASHRAE suggests static loss limits of 0.08 inches to 0.60 inches per 100 feet of duct run, up to 15,000 CFM. Above 15,000 CFM, ASHRAE suggests limiting velocities to less than 4,000 feet per minute and the corresponding friction loss. ASHRAE's duct design procedure. ASHRAE provides a guideline procedure for duct design in Chapter 21 of the 2013 Fundamentals. It is a 10-step process in outline format and provides additional references to other sections inside the chapter, as well as other ASHRAE documents. It is a great reference as a starting point and can be used as a checklist. In Step 1, you locate the mechanical room or air handling equipment. ASHRAE provides guidance for best, better, fair, and core layouts. ASHRAE suggests balancing supply and return air paths with sound isolation. Their best configuration has the mechanical room located between elevators, toilets, and storage rooms. You can see it on the upper left. The toilets and the storage rooms provide paths of return and supply air while isolating the tenant space from the mechanical room sound. The pour case, located on the bottom right, has the mechanical room backed up against a staircase with 3 walls exposed to the tenant space. The room layout has the greatest opportunity for acoustical issues from the mechanical equipment, but allows the most freedom for supply and return ductwork. Step 2, design air diffusion. In Step 2, you'll lay out room airflows, select diffusers, and determine zoning of those rooms. Step 3, selected duct shape. Standard ductwork is produced in round, flat oval, and rectangular shapes. When selecting the best duct shape for a project, there are 5 main points to consider. Space constraints are the #1 consideration. If the duct does not fit inside the available space, the other points really don't matter. In this case, in most buildings in the U.S., rectangular ducts are installed because there is limited space in the ceiling plenum. Next point is pressure class. Design standards for pressure class are available for all 3 shapes under positive pressure. It is worth noting that construction standards are not available for exhaust or negative pressure systems for flat oval ductwork though, and this should be considered. When it comes to sound resistance, round duct has the greatest resistance to low frequency noise, followed by flat oval. Rectangular ductwork has the least resistance. The perimeter of a duct is also a concern. It is important because it directly relates to the amount of insulation required and thus the cost of the insulation to the project, as well as the greater the perimeter of a duct, the larger the surface area, and thus the greater the duct heat transfer to supply air heat gain or loss depending on system. Weight, because also round ducts are the most efficient shape in regards to perimeter and equivalent diameter, they utilize the least amount of sheet metal for a given airflow and therefore have the least weight per airflow. The second most efficient is flat oval, followed by rectangular. If we review all these considerations in concert, we see that round ducts are the most desirable choice, but due to size and space limitations are not always selected. The next would be flat oval, and then finally rectangular. Step 4 is sketch the layout. Before starting the layout, you need to identify areas to be avoided. Sound-sensitive areas, such as conference rooms, need to be avoided. If they cannot be avoided, you need to plan to decrease duct velocities to control sound generation in these areas. Impenetrable walls like shear walls or fire stair enclosures should also be avoided. IDF and server rooms generally have restrictions for trunk ducts over them. Exposed ceiling areas and low structure or high ceiling areas when possible. When sketching out the one-line ductwork, minimize fittings. Fittings increase both cost and sound of duct system. Avoid closed coupled fittings, as duct pressure losses increase dramatically in these cases. Step 5. Section and number. Dividing systems up allows for documentation and quicker changes if required. Identify required items that will provide pressure drop to the system at this time, such as fire smoke dampers or balancing dampers, splitters, duct heaters, silencers, fittings, air monitoring stations, terminal units, diffusers at grills, etc. Determine a procedure for where fittings will be accounted for and stick with it. For example, I always accounted for fittings or takeoffs at the end of a long duct run. This way, I never double dipped. The static loss for those were always accounted for in the upstream duct section. Step 6. Zoning and airflow. At this point, you record airflow volumes on the sketch. Things to keep in mind while you're recording these airflow volumes. When designing a VAV system, consideration must be given to changing diversity of the load. This is generally, but not always, refers to the skin load requirements or loads of a building. As the sun progresses throughout the day, the airflow required by the perimeter zone will change and the supply air totals in the building will move around to follow the sun. If you are utilizing duct runouts for your primary air system, those duct runouts will need to be designed for the sum of the peaks of that runout. If you're using a main duct loop instead for the primary air, you'll need to include the diversity in those calculations. Skin diversity can be determined by reviewing the system peak versus the sum of the peaks reports or similar reports from your load program. After diversity is calculated and accounted for, the airflows are totaled back to the air handling units. Step 7. Duct sizing. At this point, we're going to utilize one of the duct methods that we discussed earlier. Select the most appropriate for the design of your system. Airflow should have been calculated in the previous step. At this point, you add both duct velocities, unit friction, straight duct length. You'll calculate and record fitting takeoffs and losses. Include miscellaneous equipment pressure drops, such as fire smoke dampers, heating coils, air monitoring stations. Total system resistance for the longest path or the greatest pressure drop should be identified at this point. Resize ducts to provide as close to an equal friction system for each branch from the terminal unit back to the fan. For single duct VAV systems, dual duct, and parallel fan powered terminal units, calculate pressure drop all the way through the diffusers. For a series fan powered box, provide minimum pressure across the unit air valve for design airflows, as the terminal unit will provide pressure for the secondary distribution through the diffusers and grills. Step 8. It's time for the detailed layout. Lay out the duct system in detail, or double line. Verify system clearances to plumbing systems, fire sprinklers, structural, and architectural features. When reviewing clearance, remember to account for bracing, duct connections, and insulation height. A good design practice is to include a section detail on the design drawings with designated zones for fire suppression, ductwork, and lighting. If rectangular ductwork is being utilized, it can be transitioned to larger aspect ratios to fit over impediments or high ceiling areas. As a rule of thumb, though, I never exceed an aspect ratio of 4:1. Another method for transferring over limited height areas is to utilize multiple duct runs. Examples are given on Table 7 of the ASHRAE Fundamentals 2013, Chapter 21. Step 9. Checks. At this point, you should review the routing versus the original schematic and duct sizing calculations. If the system varies, modify calculations to match the new layout. Have the ductwork system reviewed for objectionable sound levels if high velocities were required. If you find that you have high sound levels, some options for mitigation of these levels are as follows. Utilize internally lined ductwork. Double wall construction sometimes can reduce sound. Sound attenuators, or even duct lagging are options available to you. When system resistance is calculated, a fan selection can be made. Make sure to include pressure drop for filters and any intake louvers. Both the supply and the return air pass all the way back to the equipment. Verify selected fan and motor are in compliance with the local energy requirements. If the fan power is out of compliance, it will require ductwork redesign to lower your pressure drop of the system. Review system balance, making any final changes to provide an approximately balanced pressure loss through all branches. Let's look at specifications. What should be included in ductwork specifications? Ductwork construction standards are of course at the top. I always preferred SMACNA. The current edition is the 3rd edition. It is HVAC duct construction standards, metal and flexible. Pressure class should also be addressed either on the plans or in the specifications. By listing pressure class by system, you can minimize the cost of construction because the higher the pressure class of a system, the higher the cost of the ductwork. Not all systems require the same pressure class. At a minimum, pressure class should be broken up into primary, secondary, return, and exhaust system classes. When selecting pressure class, remember to review the fan selection maximum static pressure available. It will be higher than the design point. If there is a control malfunction and terminal units on a VAV system are closed, the primary fan could ramp up above operating conditions and damage the ductwork, causing a costly repair. So it's always a good idea to set your system static pressure class by the maximum available and not the design point. In duct construction standards, there are multiple methods for bracing and connecting ductwork sections. Each of these methods have a different height above the ductwork that should be considered in system clearance calculations earlier. If the available space is very limited, the designer can specify a maximum bracing connection height to fit. Be aware that limiting the choices to the bidding contractors can raise the project cost because not all connection or bracing types cost the same. Duct dimensions on drawings should be detailed, how they are designated on the drawings. In most designs, the office ductwork sizing on drawings are inside clear dimensions and do not account for liner or bracing. This should be clearly identified either in the specifications or the drawings. This will allow contractors to provide accurate pricing for the project and ensure the design intent of the project is met. Leakage rates for the ductwork should be identified in the specifications. You should also call for job site testing and verification. Inside ASHRAE Chapter 21, they currently suggest a maximum of 5%. Finally, let's look at some means of optimizing your duct design to save energy. Designing low velocity systems is a great start. Utilize 1,500 feet per minute in your primary duct runs in place of old design guidelines of 2,000 or 2,500 feet per minute. Utilize long radius turns instead of 0 radius turns. These will save a drastic amount of energy. Balancing of the duct system and recommissioning also help to maintain energy efficiency of the duct system far past the design. Equalized system design is a great opportunity for energy savings. During the design, if a particular run is setting the system resistance, Look for opportunities to decrease the pressure drop to that point. You can upsize the duct or change the takeoff location of that particular run. The greater the discrepancy between it and the next closest run, the greater the opportunity for energy savings. Poor inlet conditions can also add pressure and a decent amount of friction to your system. You should always verify terminal unit takeoffs and keep them as straight as possible. Because the primary system has the highest velocities, it also has the greatest opportunity for conservation. Runouts are a perfect example. Size runouts based on primary duct design criteria and not on inlet size. Utilize a smooth transition to the inlet size 3 duct diameters back from the terminal unit. This will allow the air adequate distance to normalize and provide a good velocity profile to the terminal unit without the excessive pressure drop. Eliminate closed coupled fittings. Fittings in line will have a multiplying factor of their friction loss and should always be avoided. Loop ducts are a good tool to minimize both installed ductwork and energy usage. By looping the ductwork, the system can move the air with the diversified load, like a skin load, around the building as the load changes. If separate runouts were utilized per exposure, or some combination of the exposures, the ductwork would have to be sized for the sum of the peaks, and the runouts would require greater pressure to fill them year-round. To where a loop duct, allowing air to transfer from both sides of the duct to wherever the design point was at any time of day, will decrease your total energy usage. Primary system static reset is another great tool for saving energy. This works by polling the different terminal units in a system by the BMS. The BMS will look at each terminal unit on a regular basis and determine which one has the greatest percentage open air valve. This is the box that will be setting the primary air system static. The BMS will decrease the static pressure until that air valve obtains a 95% open position. Then the BMS will hold that static until that air valve or another air valve opens above 95%. At that point, the BMS would increase the pressure to the system until the valves came back to the 95% position. With this system, the BMS always provides the minimum amount of air necessary to utilize all the boxes and helps to save energy the most hours of the day and most hours of the year. Because interior zones generally experience constant loads compared to perimeter zones, they will usually govern a primary air system pressure reset loop. By oversizing interior zone terminal units within manufacturer's recommendations, the BMS system will allow the primary system to reset more hours a year, saving a greater amount of energy. That has completed the webinar. In putting this webinar together, I used several reference materials, which are listed here.